Okay, so this is a theorem, first of all. So, as with any theorem, there are conditions that must hold beforehand. So, we're going to say if limit as x, now we're dealing with x, and a function, f of x, exists, then sequence, so the sequence, an equals f of n converges to the same limit. So basically, in formal terms, this will look like this. So we have our sequence, the limit of the sequence, which we just figured out how to compute. But now they're saying in this theorem that this is going to be equal to the limit of a function of x if our sequence can be represented as a function of x. Okay, so I'll get back to this when we do an example. But for now, I'll move on to a different theorem. So this is going to be the Squeeze Theorem. And that should sound familiar, but this time it's for sequences. So 4 sequences in particular. So we're going to say if, so these are the conditions that must hold beforehand. So basically the sequence Bn must be less than or equal to sequence An, which must be less than or equal to Cn. Okay, and then and of course we have to have this n is greater than big M, right, because that's part of our limit definition for sequences. And then we're also given, so this is all like if this and this, and limit as n goes to infinity of Bn equals L, which equals the limit as n goes to infinity of Cn, then we have our big then, and as you might conclude, this is like the sandwich or squeeze theorem. So if the lower and the upper sequences, in this case not functions anymore, but sequences, if they both go to a certain limit, and that is the same limit, then the middle one must go to the same limit as well. So then we can conclude that limit as n goes to infinity of the sequence an must equal L as well. Alright? Okay, so now for a few more limit laws. I know these are in your book, but I just like to write them out so you're more familiar with them. So limit laws now for sequences. Okay, so we're kind of given that we know the limit of as n goes to infinity of the sequence an equals capital L. These are just assumed to be true, and we're just going to find properties between these two limits of the sequences. So let's say this is capital M, and that's not, well, I'll make it a different letter. That's what they say in the book, but let's go with K, capital K, alright? So you don't get confused with the other big M. So basically, some of the limit laws just say that these limits share some properties. So let's say you were to add the two sequences or subtract the two sequences, okay, from each other, and then that would just mean that the limits the limits are related by the same function. So that'd be L plus or minus K, depending on whether if you're adding the sequences, then it'd be L plus K, and if you're subtracting, then it'd just be L minus K. So that's pretty simple. And then the other ones, let's see, the next one, the limit goes to infinity of an times bn. Then, as you might assume, that would just be L times K. All right? And then we have similar for dividing. So if you have an divided by bn, then our answer would be, the limits would be related in this way, where, and then we have the condition that k must not equal 0, right? Because then that would be undefined, which is not good. And then the last one, limit as n goes to infinity. So now we're going to introduce a different letter here. So c times one of the sequences, where c is a constant. Then that just, let's see, c is a constant, so c constant, So that's just some number, right? So then that would just be, we could bring C outside. C goes outside the limit, and then we just have L, right? Whatever the limit tends to. Okay, so that's it for those. And now we'll go on to something called a geometric sequence. So, geometric sequence. Okay, so geometric comes in the form of, here's the general term, we have an equals c times r to the n. So c and r are both constants, and they have to be non-zero constants, not equal to 0. Okay, because then that would kind of just make every term 0. And that's not very interesting. So what's interesting about geometric sequences are the limit of them. So the limit as n goes to infinity of this sequence, an, is equal to the limit, and I'm just going to replace an with what it actually is, but it's represented by c r to the n. So this can actually equal technically 4 different things, depending on what your r is. So c is just a constant, and c is just the constant that is in front, so technically you could bring that out in front here, and it doesn't do a whole lot, it just sits there, but r is the important one. So if we have, let's say, we said r can't be 0, but let's say it's between 0 and 1, all right? It's some fraction, so like 1/2 or something. So if you think about it, if you plug in like a 1/2 in this spot, then we'd have, let's say, c times some constant times 1/2 to the n, and n is going to infinity. So this number is becoming super, super, super small because you get 1/2, then 1/4, then 1/8, and you keep multiplying the denominator by 2. So that makes the denominator huge, and the 1 just stays 1, right? So this will actually tend to 0 when r is between 0 and 1. And similarly, let's see, what if r is between 0 and -1 on the left side? If we had a -1/2 here, then we would get the same thing going on, right? Because then we have a fraction, and any fraction multiplied exponentially times itself, then that's going to go to 0 as well. Okay, let's say we have, okay, now we'll say r equals 1. And if r equals 1, then that would just be, okay, I don't know what this arrow is doing here. Let's try this one. We have c and then r equals 1 to the n. So 1 to any power, that's just still going to be 1. So then our limit just equals c. Okay, so that's a nice one. Let's see what else we have. And then let's say r is greater than 1. All right. Then we get that r is going to be, let's say it's 2 or something. 2 to the, or any constant to the exponential power greater than 1, which is not a fraction, that's just going to go to infinity, right? That it's going to not have an upper bound at all. And the last case, I know there's a lot of them, but if r is less than or equal to -1, let's just say it's equal to -1, and it holds true for anything with a negative sign in front that's not a fraction. If we have like a -1 here, if n equals 0, then this part here would just be 1, so then we get c. But then if n equals 1, then we would get that r is -1, so then that would be -c. And what ends up happening is you get like c and then a -c, and then c and then a -c. So this actually, because there's no in-between values, that's going to diverge. Okay, because it's just going to flip between the positive and the negative and the positive and the negative, and there's no like decisive value. Okay, so let's see, we'll go on to the next slide, and this is another theorem. I know if you've looked through the section in the book, there are a lot of theorems in this section, but they're all pretty important. So that's what I'm going to stress on, that's what I'm going to emphasize in this video, as opposed to examples. I mean, I'm going to do some examples, but mostly theorems and explaining concepts. So this theorem says if f of x is continuous, okay, I'm just going to abbreviate, continuous, and limit as n goes to infinity of an equals L, and then here's our big then the following is going to be true. So then we have limit as n goes to infinity of f of an equals the following: f of the entire limit itself, the limit of the sequence, okay? And then this, since we assumed this part, then we could just plug in L for the parentheses, so f of L. So this, in a way, they call it bringing a limit inside of a continuous function, inside continuous function, okay? So I will do an example of this, because right now this is kind of vague and we don't really know what's going on. So I'll do an example on the next slide.